name is Priyank Kalla. I'm a faculty member in the ECE department. I work in computer engineering. I have to apologize. I completely forgot that we were having this meeting today. I just looked at my email and I saw John's message. The other problem is that my computer has sort of crashed. I gave it for repairs. I just got it back yesterday, but while they repaired everything, the mic has gone, is not functional anymore. So I have to do it on my iPad. So I'll basically just take a couple of minutes. Are you guys able to see my screen?
Yeah, yes, we can see it.
Okay, perfect. So I'm actually looking to recruit a couple of students. I have two projects where I need some student help. One of the projects is basically related to design and automation with in integrated optics. In particular, I'm basically interested in building some test structures, okay, in silicon-based integrated optic. So these test structures are going to help us do design debug, okay? So I'm interested in people helping me build debug circuitry. So in general, I've had former students who have actually built, who've built some design flows. And one of the design flows that they built was mostly for synthesis. So they actually used some sort of, given a computing architecture, they designed logical switching devices through which they can actually do some optical computing, just like you do it with digital logic. Okay, and the technology and constraints are coming from the foundry. So foundries are suppose giving us pre-designed blocks such as switches and route switching devices and resonators and waveguides to build interconnects. So we build algorithms to actually do some synthesis and do place and route. And silicon-based integrated optics is very sensitive to thermal, thermal variations in the substrate. So that actually causes modulation of refractive index and it causes problems in computation. So this sort of a device flow has actually been built. So what we now want to do is here we want to add some sort of design and debug circuitry. So once a chip is designed, right, before you actually send it out to the market, you have to test whether there are any problems in the in the functionality. The problem is that once a chip is available, we only have inputs. So in this particular case, we will basically have lasers coming in and we may basically have photodetectors, okay, or the other way around. So this is where the grating couplers are. This is how you bring light onto the chip. These are switching devices which are basically built using ring resonators. And here you have some detectors. So once this chip is fabricated, you have access only to the inputs and outputs of the system, right? So our objective is to actually, if something goes wrong in between, how do you figure out, this is a very small circuit, but in large scale circuits, how will you figure out which of the devices has gone bad? And is it possible to actually go back and tune any of these devices to fix them, to get the circuit to work, okay? So our objective is to actually identify what kind of debug circuitry to design and where do we place them. So that's one of the topics that we are looking at. And in general, the defects can be either logical design errors, or they can also be manufacturing errors. So we actually have to compensate for manufacturing defects. So as you know, there is fabrication, uncertainty in the fabrication process. So these, how do we actually bring these devices to work under the presence of, manufacturing variations? So those are some of the things that we are looking at. So this, you can actually, here's a picture under the microscope. You can actually see University of Utah's logo. So, this was a small experimental chip that was designed. So this chip was actually designed using the CAD tools that were built by one PhD and one master's student of mine. It's a simple adder. You can actually see sum and carry out signals. Okay, but the deal is that all this placement and all this routing was actually done automatically. And as far as the routing, etc., is concerned, there were some constraints on how do you actually do this routing so as to minimize losses and things like that. Okay. Another student of mine actually did some analysis on given hotspots on this chip, how to actually see how the thermal gradient computation over the entire signal, and then try to actually predict the operation of each of these devices. Okay, so now we want to do something similar with some models of manufacturing variations and things like that. So this is one of the topics you can think about: design and debug, or design for test of silicon-based integrated optics. That's one of the topics that I need some help with. Okay, and another topic that I'm working on, which is actually very, very different from this, is related to design and verification of cryptography systems. Okay, so over here, what I'm showing you is a curve, which is basically called an elliptic curve. So all of you guys use cell phones, right? So when you switch on a cell phone, it connects to a base station, and the first thing it does is authentication. It authenticates your device, right? In order to do that, it runs an algorithm, which is basically called the elliptic curve digital signature algorithm. So when you do that, how does, this is basically looking at pure classical mathematics. What this is showing here is you have 2 points P and Q. If you add P and Q on this elliptic curve, it basically means that you have to compute this particular point R. So this computing of P plus QR is one of the most fundamental operation on elliptic curve. So you use encryption, decryption, authentication. They basically use this type of point addition circuits in hardware, and then they build crypto processors that will basically make use of these primitives to do some sort of computations. So the way it works out is that this is actually a very power hungry. So in general, these elliptic curves are a standard. So there is an institution called NIST, which basically specifies that you use an elliptic curve and you do it over a finite field of 2 raised to k elements. So this k is basically the operand word lengths. Okay, and NIST specifies that these operand word lengths go actually from 163-bit operands all the way to 571-bit operands. So if you use smart cards or things like that, the smallest operand size that you want to use is 163 bits. So these type of designs, when you implement them in hardware, right, they are very power hungry. Usually these guys are implemented using polynomials. So this is translated from a Cartesian coordinate into a polar coordinate system, and from there you can basically write them as polynomials. So you have these 3 points. So if you add these 2 points, you get an x3, y3, z3, 3 coordinate point. So how would you design circuits for these such that they will actually work in extremely low power mode, so that they could actually be powered by RF and things like that? So that's one of the things when you design such complex systems, you have to verify or certify that, yes, the circuit that I've designed is basically conforming to my NIST specification. Otherwise, who will buy it, right? So that's one of the type of things that my group has been doing. And now we want to extend this to this topic of what is called fully homomorphic encryption. So this is one of the new privacy data preserving encryption transformation that the world is looking at. If you do a search on fully homomorphic encryption, you will actually find a lot of information on the internet. Unfortunately, most of this is still done only in software because it is extremely complicated to build custom circuitry. So my interest is actually in building custom circuitry to do fully homomorphic encryption, okay, and in low power. It also has other implications, okay, that it is it should not be very susceptible to post-quantum crypto attacks. So we want to preserve those properties when we actually do custom hardware-based encryption. So this is another project that I'm interested. I want people to join my group. We will basically build the algorithms or CAD techniques to design circuits like that, and and build CAD tools where you take polynomial specifications like this and directly synthesize circuits. Okay, that's basically the two areas that I need some sort of help with.